Hi guys, I'm Andrew Biden.
I am Amin Yadav.
I am Max Potasevich,
I'm Tevin Chen.
And I'm Zachary Fallender.
and we are the Wailing Whales, and this is our lizard tail inspired robot for versatility improvement through yaw control.
Our design was biologically inspired by a lizard tail and the control from the tail while the lizard is in motion. Lizards move their tails when stabilizing during several types of motion using net zero angular momentum maneuvers. The hypothesis of this paper is that a tail-controlled robot could stabilize itself in several scenarios, such as falling, going over bumps, or moving from surfaces of one slope to a different slope. To look at the lizard mechanics, researchers recorded a lizard during jumping and observed the body angle relative to the angle of the tail, so they could observe this net zero angular momentum maneuver in action. Additionally, they tested their own robot with a couple of different tails, namely a flywheel with a weight on it and a tail with a singular weight at the end of it, simply actuated by a servo. Each test that they conducted, which was falling, going over bumps, or moving from one slope to a different slope, resulted in the robot being able to change its body angle relative to the angle of its tail and complete this net zero angular momentum maneuver, and thus the hypothesis of tail-controlled motion in lizards was not rejected. We decided to build a tail of a lizard very similarly to how one actually functions. So we chose to have a segmented tail similar to how bones are connected in an actual lizard's tail, actuated by a servo, which was connected to a flywheel that would then spin and change the location of the tail and overall the location of the center of mass of the robot. The main base plate was meant to connect to the base robot itself and then also lay out a location for all of our electronics to go. This was constructed out of PLA since it's lightweight and allowed for the correct mounting locations of everything relative to everything else, as it was all designed in CAD beforehand.
In designing the tail, we chose to go with a segmented approach, mimicking the vertebra-like segments of an actual lizard's tail, which is basically just an extension of its spine. The segments connect together via keyed slots and connecting pins, with a small protrusion on the top of each connecting pin to ensure that the tail segments remain attached to each other. Each segment has small hoops on either side to allow for fishing line to be threaded through and tied off onto the final segment, enabling tail actuation by tensioning the string on one side while detensioning the string on the other. Additionally, each segment has a small cutout portion, allowing for weights to be added in the case that the inertial effects caused by the PLA tail on its own were not significant enough to stabilize the robot's motion. After early testing, we found that the weights were not necessary and opted not to use them in the final design. One thing to note about tail stabilization in lizards is that the optimal tail length has been found to be roughly 10% longer than the lizard's body length. Therefore, we chose to use 4 segments, each segment being about 2 inches long and having a fairly significant amount of overlap with the adjacent segments, giving us a total tail length of about 6.5 inches. This is roughly 10% greater than the 6-inch body length of the robot, meaning we should be able to achieve optimal stabilization. The tensioner wheel used to actuate the tail consists of a round disc with 2 pegs, which the pieces of fishing line on either side of the tail are tied onto, as well as a groove to guide the line as the wheel rotates. The wheel is turned using a servo motor, causing one of the pegs to be pulled away from the tip of the tail and the other to move towards it, and the resultant tensioning and detensioning of the strings causes a natural curling of the tail to either side.
This is a list of the electrical components that were used in the creation of our robot. We used an Arduino Pro Micro in order to do the overarching calculations and overall control of the robot. We used an IMU in order to receive the angle measurements from the robot. These were calculated based on the gyroscope positioning, the accelerometer, and the magnetometer that's included in the MPU. In order to create our motion, we used a SparkFun motor driver. This was given to us in our development kit, and we saw it fit to use for the robot. We used a Bluetooth module in order to receive inputs from the user, where we are able to activate our robot, stop it, or change our zeroing position. We utilized the Kamigami robot chassis in order to make use of their motors, which were then again controlled by the SparkFun motor driver. In order to control the tail, we used a servo motor that was controlled by the Arduino and a battery pack that supplied 6 volts to the entire system, thus powering the system. In our programming, we gave the option for an individual to select from 3 different options. A 1 would give the user the ability to activate the robot and move it in a straight line with the tail doing any correction. A 2 would stop the robot just in case of a runaway, and a 3 would reset our zero angle to whatever angle or whatever direction the robot was currently facing. So in our program, we continuously receive z-axis or yaw information from the MPU, and from that information, we are able to calculate the deviation from 0 or the starting angle of our robot. And any deviation from that zeroing position resulted in motion of the tail. So as previously mentioned, the tail motion is controlled by a servo motor, and the motion of the servo is inversely proportionate to the direction of the angle. So that means if there's a negative angle, the tail moves to the left. A positive angle read on the MPU, the tail moves to the right. This different inverse direction to the angle creates or allows for the robot to move in a straight line.
So talking about the robot modification, we ended up attaching functional tape to the face of the robot to increase the friction against the surface. So whichever surface we use, especially that like the tile surface is pretty hard for a robot to use with the plastic feet. So we attached the functional tape, which helped the robot to stabilize really well. And of course, the addition of the tail itself, as stated earlier, it acts as a counterweight to the robot. It has 4 small segments into it, and it forms a tail, and then around the tail we have attached fish line for stabilizing it. So it helps with the stabilization of the whole robot by maintaining the total moment of inertia. As the robot tends to move in a certain direction, the tail tends to move in an opposite direction to help it straighten it and to stabilize it in a particular direction. So next we have the functional robot of the video itself. So as you can see, with the moment of the accelerometer itself, the tail is moving with it, and you have the perfect example how it functions. Next, we have another functional video for you. It's going to be a really short one. All right, so as you can see, the tail itself moves in the opposite direction of the rest of the body to stabilize the whole robot itself.
As shown on the slide, the robot is set to run a distance of 5 feet. At the end of the run, an offset distance B is measured. To account for a variety of surface friction, tests is conducted on 5 different surfaces, including marble, cobblestone, carpet, concrete, and grass. However, due to time constraint, the modified robot was only tested on 2 surfaces, which are tile and carpet. The experiment results do meet our expectation with improved versatility on both of the surfaces tested compared to the original robot. You can find more detailed data collection in the file final data plus robot operation code. To conclude, the experiment result do meet our expectation. The modified robot with added friction on its legs, along with the tail, has made the robot successfully be able to correct itself when it detects an offset. The current model features a tail with only movement on the horizontal direction. Our team think the future work can emphasize on a multi-dimensional movement tail that can be very impactful when it comes to robots encountering tough terrain. And that concludes our presentation.